Alright, so in this section, we're going to be discussing alternating series. So notice that a lot of the tests we've talked about so far, kind of like the comparison tests, they only apply to series where all of our terms are positive. So in this section, we'll learn how to deal with alternating series, right, where our terms alternate between positive and negative. And so a lot of times what they're going to look like is something like this, right? There may be other things in here, but the main thing to focus on is that we're going to have some negative number to the n plus 1, to the n minus 1, something like that. That's something where when I see that, I already start thinking about, okay, this is going to be an alternating series, so what's happening here? So what we want to focus on is, when does this thing converge? So we'll start with this thing called the alternating series test. So suppose we're given something like the sum from n equals 1 to infinity. Now to reiterate, we don't have to start at n equals 1. We could start at n equals 0, n equals 2, stuff like that. And we're going to have something that looks like negative 1 to the n. Again, remember this could be negative 1 to the n, negative 1 to the n plus 1, negative 1 to the n minus 1. And then times a sub n, where a sub n is going to be some sequence, right? So in this example right here, I would say that our a sub n is 1 over n, right? Because then I have something that looks like this infinite sum of negative 1 to the n plus 1 times my a sub n. So the alternating series test is going to be used when our a sub n is strictly positive. So if I look at this a sub n right here, right, 1 over n, whenever I'm plugging in n equals 1, 2, 3, so on, we're getting all positive terms. Now, this series will converge if it satisfies these 2 points right here. The first one is that we need for our sequence to be strictly decreasing, right? So if we look at 1 over n, we'd have 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. So we can see that this sequence, a sub n, is decreasing. The next thing we need is that the limit as n goes to infinity of a sub n is equal to 0. Right, basically that our a sub n sequence is converging to 0. Well, if we look at the limit as n goes to infinity of 1 over n, this would give us 0. So what we've proven right here is that this alternating series converges. Right, so to reiterate, I made sure that our a sub n sequence was positive. Then I checked to make sure that our terms are decreasing, and that the sequence is converging to 0. And so now let me show you a little illustration of why this is true. So what I'm going to do here is I'm going to zoom out just a little bit. Okay. So actually, let me zoom back in. So that's going to cause some problems. What I've done here is I've taken some series. We don't know what these b sub n terms are, but I've just written this out as a possible alternating series. And all I'm telling you here is that all of these terms are positive, and that this sequence b sub n is decreasing to 0. Okay, and so the important things here is that we're decreasing, right? That's one of the things we need to satisfy. All of our terms are positive, and we're decreasing to 0. So we've satisfied the 3 things we were talking about above. Now let me show you why this thing actually converges. Let's take a number line, right? And here's 0. We know that one way to look at a series, right, our definition of a series, is that it's going to be equal to the limit as n goes to infinity of s sub n. And so I'm going to start looking at these partial sums. Let's take the first one, which is S1 equals B1, right? It's just S1 is the first term in the sequence. And so let's say that B1 lies right here. then what I'm doing is I'm traveling from 0, I'm adding to B1, right? So this would be my S1. Now, S2, what we need to do for S2 is we need to subtract off B2. And here's all we know about B2. We know that B2 is positive, so that tells me that I'll be headed in this direction from B1. And we know that B2, we know that its value is going to be less than B1, right? So what I want to look at here is that B sub n is a sequence, right? So it looks like B1, B2, B3, and so on. And that B1 has to be greater than B2, which has to be greater than B3, and so on. So what that tells me is that we can't go to 0, we can't go past 0, because then this maroon line would be greater than or equal to the distance of the green line. So what this tells me is that we have to travel maybe somewhere back to, say, here, right? If B2 lies here, then I'm subtracting off B2, so that would mean that S2 lies right here. Now I'm going to add B3. Right, so we'll use a blue line right here. Make this a little bit thicker. Okay, so we'll use a blue line right here. And we know that B3 has to be smaller than B2. Let's say B3 is right there. So then now, I'm going to add on this B3 line. And so that means that S3 will lie right here. And we'll keep on doing this over and over again. So maybe B4 is like right here, which tells me that S4 would be right here. And now let's say that B5 is right here. So that tells me that maybe S5 is right here. And so notice that the distance of these lines, right, the green line, the maroon line, the blue line, the purple line, the orange line are getting smaller and smaller until maybe we're converging to our S sub n being maybe somewhere right here, somewhere in this range. Okay. Another way to look at this is maybe like imagine you have 1 minus 1/2 plus 1/3 minus 1/4, on and on and on. If you start looking at that using this little line scenario, then you'll see that we're getting closer and closer to some point. Okay, so that's just a little picture of why this is true. Now, let's look at example 1. So what we want to do here is we want to use our alternating series test because we see that this is an alternating series. By the way, we're still doing, every time we look at these problems, I've constructed them to where the test for divergence probably isn't going to be helpful. But you should still be using the test for divergence first, as it's kind of like a quick way for us to check if something diverges or not. But in example 1, the test for divergence will fail because our limit will go to 0. So let's look at our alternating series test. Well, here, our a sub n would be equal to 1 over square root n plus 3. Okay, so here's what I notice. N is starting at 1. And so as I plug in n equals 1, 2, 3, 4, 5, we have a positive term on top and a positive term on bottom, which tells me that a sub n will always be greater than 0. That's the first thing we need for our alternating series test. The next thing we need is that this is going to be strictly decreasing. Okay, so let's start looking at these. We'd have 1 over square root 1 plus 3, so it'd be 1/2. Or we could just call this square root 4. I think it'll be a little bit easier to see that way. And then we'd have 1 over square root 5, 1 over square root 6, 1 over square root 7, and so on. And so we can see that our denominator is getting bigger and bigger each time, which means that our fraction's getting smaller. So this tells me that a sub n is decreasing. That was the second thing we needed. And then the third thing we need is that the limit as n goes to infinity of a sub n is equal to 0. Well, if I look at the limit as n goes to infinity of 1 over square root n plus 3, that will indeed give us 0. And so what we say is that this series converges by the alternating series test, which we're going to abbreviate as AST. Alright, now let's look at example 2. Example 2 here is a little bit more difficult because they haven't given us the formula for our series, but we can get it pretty quickly. So the first thing I'm going to notice is that we're alternating between plus and minus. So that tells me that this is going to be equal the sum from n equals 1 to infinity. So the first part is to figure out, is this negative 1 to the n or negative 1 to the n plus 1? Well, since my first term is going to be positive, I'm going to make this negative 1 to the n plus 1. The next thing I'm going to look at is, okay, let's look at these fractions. There's always a 1 on top, so this is going to be times 1 over, and then if I look at the bottom, we have 2, 3, 4, 5, and so on inside our natural logs. So to me, that looks like the natural log of n plus 1. Now notice, I could have written this a little bit differently. If I did the sum from n equals 2 to infinity, then this right here could have just become n, and then our exponent up here would have changed to n as well. Right? So there's different ways to write this, and they'll all work out the same for evaluating whether it converges or not. So now I need to look at our three things that we need. Okay, 1, what is a sub n? So a sub n, yikes. Sorry about that. Alright, so a sub n, oh, wrong color. A sub n is going to be equal to 1 over the natural log of n plus 1. Okay, so now I want to figure out, is a sub n strictly positive? Well, we know we're always going to have a positive 1 on top, and so now I'm just worried about, is the bottom part of this fraction positive? Well, we know that the natural log of 1 is equal to 0. And we know that we're starting at n equals 1. So the smallest value we'll have on bottom is going to be the natural log of 2. Well, this must be greater than the natural log of 1. So that tells me that the natural log of 2, the natural log of 3, the natural log of 4, so on, they're all going to be positive. So what we've shown here is that a sub n is always going to be greater than 0. Now we can also look at, so we'll have 1 over ln2, sorry, let me start over here. 1 over ln2, 1 over ln3, 1 over ln4, and so on. And so we can see that this denominator is getting bigger and bigger, which means the fraction is getting smaller. So we do have that a sub n is decreasing. And then finally, we'll look at the limit as n goes to infinity of a sub n. So this is of 1 over the natural log of n plus 1. Well, our denominator here is going to be going to infinity, which means that the fraction itself has to be going to 0. And so then this tells me that our series converges by the alternating series test. Alright, now let's look at example 3. So again, our first step is to identify our a sub n. So it's just going to be everything except for the negative 1 to the n. So we have that a sub n is equal to n squared over 1 plus n squared. Okay, well n is getting, we're going to have positive numbers on top and bottom. So we know that a sub n is greater than 0. Now I want to look at, is this thing decreasing? Okay, so notice that n squared will be, so let's see, let's look at these terms. If I plug in 1, we're going to have 1 over 2. If I plug in 2, we'll have 4 over 5. If I plug in 3, we'll have 9 over 10. If I plug in 4, we'll have 16 over 17. Alright, and so what we have here is a sequence that is clearly not decreasing. Right, just going from 1/2 to 4/5 is enough. We know that this thing is not decreasing. And in fact, it's going to be increasing the entire time, so it's not like we can split it up into 2 parts and get a decreasing part. So what we should be thinking here is to use our test for divergence. Well, when we take the limit as n goes to infinity of -1 to the n squared over 1 plus n squared, this is not going to exist. And so we can say that it diverges, our series diverges by the test for divergence. Now let's look at example 4. So for example 4, this one's a little confusing because we're not sure what our a sub n should be. Well, one key thing is that we can actually turn this into a geometric series. Right, so I'm going to rewrite this as the sum from n equals 1 to infinity of -1 to the n minus 1 over 2 to the n. Right, I just used this negative exponent right here and brought the 2 to the n to the bottom. And so here what we have is that this would be equal to the sum from n equals 1 to infinity of, well, let's see, remember, we're starting at n equals 1, so we want this to be in the form of a times r to the n minus 1. So we'll call this 1/2 times -1 over 2 to the n minus 1. And so we know that this is going to converge because r is equal to -1/2, and so its absolute value is less than 1. But let's try to look at this as a alternating series test problem. So what we'll use is that a sub n is equal to 1 over 2 to the n. So then we know that this is always going to be greater than 0. We know that it's decreasing because the denominator is getting bigger every time. And then we'll look at the limit. So limit as n goes to infinity of 1 over 2 to the n. We know that's going to be equal to 0. So we can also say that this converges by the alternating series test. So that's just kind of 2 different approaches to this problem. If we're just being asked for convergence divergence, we can use either the geometric series properties or the alternating series test. Now, if I want to know what this actually converges to, then the alternating series test isn't important anymore because it doesn't give me the value that it's converging to. Alright, now we'll move on to example 5. So for example 5, again, the first thing I'm going to do is figure out what my a sub n is. So we'll have that a sub n, is equal to 2 to the 3 over n. Okay. So this is going to be the same thing as the nth root of 2 cubed. And so we know that this is always going to be positive. The next thing I want to check is that it's decreasing. Well, we're taking nth roots, right? So if you take, say, some number like 8, if I take the square root of that, that's going to be somewhere between 2 and 3. If I take the cube root of that, it's going to be equal to 2. If I take the fourth root, it's going to be smaller than 2. Right, so as we take higher power roots, our number's getting smaller and smaller. So we can say that a sub n is decreasing. And then now we'll check our limit. So we have the limit as n goes to infinity of, let's see, this is going to be 2 to the 3 over n. Well, let's see. That would be the same thing as 2. And then we'll bring our limit up here. So limit as n goes to infinity of 3 over n. Well, this limit is going to go to 0. And so we're going to get 2 to the 0, which is equal to 1, which tells us that the alternating series test is not the right thing to be using here. Instead, we can say that this is going to diverge by the test for divergence. Right, so this is just another reminder that if you're trying to apply the alternating series test, and you get something that either isn't decreasing, or you get something where the limit doesn't work out like we want it to, then you should probably go back and check your test for divergence if you didn't already check it. Okay, and so now let's check out example 6. For example 6, the first thing I do is identify my a sub n. So we get that a sub n is equal to the natural log of n over n. Alright, well, we checked before that the natural log of 2, the natural log of 3, all of those are going to be positive numbers. And then we'll be dividing by positive numbers, so this is always going to be greater than 0. Now I want to check for that it's decreasing. Okay, so this one's a little bit difficult to see that it's decreasing. But what I want to look at is, let's look at the growth rate of these two functions. So on top, we have the natural log of n. Now, a quick reminder that when you take the derivative of something, you get the slope, or the rate of change. So this is going to grow at a rate of 1 over n, because that's the derivative. Okay? And then n, well, that's going to grow at a rate of 1, because that's the derivative of n. And so now I want to look at, okay, well, what's going to be bigger, 1 or 1 over n? Well, the only way that 1 over n is greater than or equal to 1 is if n is less than or equal to 1, right? If I take, n starting at 2 here, then we'll have stuff like 1/2, 1/3, 1/4. And so all of these growth rates are going to be smaller than 1, which tells me that my denominator is getting bigger faster than the numerator, right? It just means it's growing faster. And so that's what's going to tell me that this thing is actually decreasing. Okay, if that doesn't click for you, then you can look at actually calculating these values, right? So we'd have ln of 2 over 2, ln of 3 over 3, ln of 4 over 4, and so on. And so if you plug these into a calculator and calculate them, you will see that this is really decreasing. So I'm just going to say a sub n is decreasing. Okay, now I want to look at our limit. So let's take the limit as n goes to infinity of ln of n over n. And so what I'll use here is L'Hospital's rule. So we'll get the limit as n goes to infinity of 1 over n over 1, which gives us the limit as n goes to infinity of 1 over n, and this will give us 0. Which tells us that our series converges by the alternating series test. Okay. Now, remember previously that we did the integral test and then we approximated what the sum was going to be with our partial sums. And we were able to kind of say how close is our integral test to the actual sum. Well, we're going to do something very similar here. So first I want to remind us that the remainder estimate for the integral test told us that the remainder, or the error, r sub n, is always going to be less than or equal to this integral from n to infinity of f of x dx. And remember, we had f of x model a sub n, right? So if we were given something like, I don't know, n squared plus 1 cubed, then our f of x was x squared plus 1 cubed. Because when x is equal to n, these two values will be the same. Okay, well now we can say if we have some alternating series that's convergent, right? So here's our alternating series and it converges. And we need that this a sub n is strictly positive. Then we can actually still estimate the sum of our series. And what we'll know is that the absolute value of our error has to be less than or equal to a sub n plus 1. So let me show you what's going on here. So let's look at example 7. The first thing they want us to do is prove that this series is convergent. Okay, so we've got a sub n is going to be 1 over n cubed. This is positive, definitely decreasing. And if we take the limit as n goes to infinity, we will certainly get 0. Right? So this means that the series converges by the alternating series test. Okay, so that's the quick and easy part of it. Now, the other part is to find this error that they're asking for. They want us to find the error when using s sub 6 to approximate s, which is the sum. Okay, and then there's another piece to this, but we're going to focus on this part for now. So for this part, whenever we're finding the error, we can go back to this remainder estimate. Okay, so remember what we needed. We needed some alternating series, which we have. This is an alternating series. We need it to converge, which we just proved that it converges. And we need our terms to be greater than 0. Well, since we used the alternating series test, we proved that it's greater than 0 right here. So we've satisfied the three things that we need here. So then this tells us that r sub n, well, our n right here is going to be 6. So this tells us that the absolute value of r sub 6 is going to be less than or equal to a sub n plus 1. So this is going to be a sub 6 plus 1, which is going to be a sub 7. Well, a sub n is equal to 1 over n cubed. So that tells me that a sub 7 is going to be 1 over 7 cubed. So what we found here is that the absolute value of this remainder, this error, has to be less than or equal to 1 over 7 cubed. Right, and so what this means is that our sum is either 1 over 7 cubed, our partial sum, s sub 6, right, this part right here. This is either 1 over 7 cubed greater than the actual sum, or 1 over 7 cubed less than the actual sum. It could be in either one of those ranges. So now we want to look at the next part of this problem. The next part was for us to determine the minimum number of terms that we need to get an error less than 1 over 150. So what this is saying that we want the absolute value of r sub n to be less than 1 over 150. But we know that the absolute value of r sub n has to be less than or equal to a sub n plus 1. So what we're really saying is that we want a sub n plus 1 to be less than 1 over 150. Okay, well a sub n plus 1 is going to be equal to, let's see, a sub n plus 1 has to be 1 over n plus 1 cubed. Right, I just got that from plugging into our a sub n formula up here. So what we're saying is we want this to be less than 150. So that would mean, 1 over 150. So that would mean that 150 has to be less than n plus 1 cubed. Okay, well if that's going to be true, then that means that the cube root of 150 has to be less than n plus 1. Okay, and if I calculate that and subtract 1, what we'll get is that 4.313 has to be less than n, which means that n equals 5 is the minimum number of terms that we have to add to get an error less than 1 over 150. Okay, and don't worry, we'll practice this again. We're going to practice this on number 8. So we want to approximate this to within an accuracy of 10 to the negative 2. So the first thing we should be doing is finding our a sub n. So the a sub n is going to be 1 over square root n. We know that this is strictly positive. We should prove that this converges. So let's just think about it real quick. This thing is definitely decreasing because our denominator is getting bigger. And we know that our limit's going to go to 0. So this thing will converge by the alternating series test. Okay, so now we can apply this new remainder estimate that we learned. And the key thing to take away from the remainder estimate is that our error, the absolute value of the error, has to be less than or equal to a sub n plus 1. And we want this to be within an accuracy of 10 to the negative 2. So we want this to be less than 1 over 10 squared, which is 1 over 100. Okay, well, our formula for a sub n is right here. So I'm just going to plug in n equals n plus 1. So we want 1 over the square root of n plus 1 to be less than 1 over 100. Which means that I want 100 to be less than the square root of n plus 1. So I'm going to square both sides. So I want 10,000 to be less than n plus 1. Which means that I want, one key thing here is we want it to be within an accuracy of 10 to the negative 2. So I'm just going to point out these little grammatical differences. Here we wanted our error to be less than 1 over 150. So that's why I'm using a less than sign here. Whenever you see within, that means that this should be a less than or equal to sign. So then this should be, I'll subtract 1 from both sides. We'll get 9,999 is less than or equal to n. And so then what we would want to use to approximate this would be s sub 9,999. So that means that if we add up the first 9,999 terms, then we will get within an accuracy of 10 to the negative 2, which would be the same thing as 0.01. All right, and that will conclude our alternating series test. And this is all that you need to watch for the class activity on Wednesday.